Anyone else have any other Lab 2 questions? I have Lab 3 related content to go over, but I know that most groups are sort of in the depths of Lab 2. So if anyone has other bugs that they want to talk through, that'd be time well spent.
Yeah, Hunter, me and Diane had a question about resetting, like when you're driving the audio codec from the FPGA. So I know it's like kind of set to, you're supposed to like press a button to reset it. And in the lecture before, you kind of talked about having like a reset PIO line. But wouldn't that then force you to like use the HBS to start it or something like that? Like, I guess, can you reset it all from just like Verilog?
It's not clear to me how you would do it all in Verilog. I think you need some interaction with the HPS. I would reset over a PIO line. I think that's the easiest way to do it.
So then we would just have like some C program that literally just like sets that PIO like high and then low. And
yeah. And you might go to the PIO examples, and like the first example on the PIO page is just a dead simple C program that sets and reads a couple of PIO ports, and you could strip that down to just writing one PIO port.
Okay, got it.
Any other issues? We've had a couple of groups that faced or are facing the issue of things looking correct in Model Sim and not looking, and then not translating to the FPGA. So I know Alex and Katie are facing that issue. Andrew, Megan, and Rohan had that issue. Are any other groups having that issue? Okay, well, that's encouraging. People have started trying to put things on the FPGA, right? You're not having that issue because you haven't put things on the FPGA, I hope. Hopefully you all saw the note on Piazza. So I have a correction to some documentation and to something that I explained in a previous lecture. If you are finding that your drum is making static noise, the issue with this might be that depending how you implement your M10K blocks, let me actually share my screen. In lecture, we talked about implementation of M10K blocks. If you implement it as shown in the HDL style guide, which is to say as shown here, this requires, after you set the read address, this will require two states, two standby states until the information is available to be read back from the M10K block. So in previous lectures, I said you had to wait one state. If you set your M10K block up like this, you actually need to wait two. And if you don't wait two, if you only wait one, you will get probably the most common symptom I've seen is a hissing coming out of the FPGA. The reason for this is the read address here, you can see in the second part of this, the read address is registered. So the fix to this, if you want to be able to read from your M10K block with only one state of delay, then you can get rid of the register on the read address. And then instead of putting your, setting the value of Q equal to mem at read address reg, where that's the register where you're using to register the read address. If you instead just set the value of Q equal to the value of mem, the mem array for the input read address, this will drop the number of states that you need to wait in order to read from that memory block by one state. So you'll set the read address, wait a state, and then it will be available on the subsequent state if you do it this way. If you do it this way, then you'll set the memory address, wait for a state, wait for another state, and then the information will be available to be read. Are there questions about that? The other, Andrew, I know that you just spent some time explaining this, but not everyone was in the room. Andrew, Megan, and Rohan just spent a lot of time tracking down a very, very tricky bug. Do Andrew, Megan, or Rohan, do you mind, I know that you just did this, but do you mind taking just like a minute or 2 minutes just to explain what the bug was and what the symptom was, just in case other people are facing similar issues?
I guess, long story short, like this is what we probably should have realized from the beginning, is that if the signal tap outputs like numerically, like you don't even have to look at the waveforms, but just like numerically, if the values don't match what you're expecting on model sim for the same set of initial conditions, like that's like the first thing you want to fix. Like what we tried to do was listen to the FPGA, see what was happening on it, and then try to reason about what the issue could have been. And then I think that led us down a rabbit hole that we could have avoided if we just tried to get signal tap value parity from the beginning. Because from there, then you can be confident that if the FPGA isn't outputting correctly, then it's probably a synchronization issue. And then by looking at that, you can probably also tell whether or not your memory outputs are correct. And if your memory isn't behaving the way you'd expect it to, then that's probably the symptom of the wrong memory cycling delay stuff. But okay. Signal tap is absolutely where you want to default to. I've converted.
Yeah, they used just about every technique in the book, and signal tap ended up being the critical tool for getting this figured out, actually looking at the traces on the FPGA. Go ahead, Megan.
Sorry, one thing I just wanted to add on is that, like, I think one part that led us to not kind of approach that first, to ignore that difference in our values, is that when you actually look at like when we looked at our signal taps, like output values from what was running on the FPGA, it kind of looked like a drum-like waveform. So we assumed it was somewhat correct values, and everything was going okay with our actual drum module code. So that's why we looked at other avenues like synchronization or memory delays, but it was a waveform that looked like what it should have looked like, but was actually not the correct value that we were wanting. And that was what was producing a noise that was not our drum sound.
And the fundamental issue ended up being an inferred latch, which does not throw an error. So this is also a reminder to everyone that every time you compile in Quartus, search your warnings for the keyword inferred or implicit. And Andrew and Megan, you also reminded me to remind people. I've gotten a couple of questions just confirming the fact that there needs to be some method of synchronization between the state machine that's running the audio subsystem and the state machine that's running your drum. And that is indeed the case.
So the thing is, we had a synchronization scheme that's different from what we were showing you before. We referenced ours from like Felipe and Sujith's working implementation, Felipe, Sujith, and Rishi, because they had theirs working, and then so we were asking them about how they did it. And like functionally, I'm not sure how different it is from ours was before, but also our outputs to begin with were wrong even after we had synchronization implemented. So I can't say for sure how necessary that is, or like how important that works perfectly fine. Because I haven't tested correct outputs with bad synchronization.
Okay, so this may not have been your specific issue, but if you don't have proper synchronization between these two things, it will cause an issue. You want for the drum to produce precisely one sample every time the audio state machine asks for it. So when there's space available in the audio FIFO, you want for your drum state machine to fill that with a new sample. If you're not careful, particularly for small drums, you will finish updating your drum far faster than the audio state machine is running. So if there's no synchronization, the symptom may be something like, maybe you hear like one pop and then limit cycles or something like this. Your drum, you'll get through the transient part of your drum strike very, very quickly and never actually hear the strike because your drum state machine will be running so much faster than the audio state machine. So the audio needs to throttle the drum. And then next week, like when you're making the biggest drum that you can, you'll push that so that the drum, you want the drum to just be finishing with an update the next time the audio wants a sample. That's how you get the biggest drum that you can. But for this week, when we're building approximately 10 by 10 node drums on the FPGA, that drum state machine will be done long before the audio system wants a new sample. So there needs to be a method of synchronization between those two things. And there are a few different methods you can think about. Some sort of simple flag works pretty well. When you finish, so you'll write to the left channel, left audio channel, you'll write to the right audio channel. Once you finish writing to both channels, you'll release the drum, allow it to compute a new cycle, but then you'll only allow it to compute one cycle, right? So the drum will compute one more cycle and then wait to be signaled by the audio system again to compute the next cycle.
One thing I want to add, just this might be interesting to you, is that I know we were talking about the bus ACK and potential latencies from that before, but from looking at the outputs on that, or just from the behavior of the state machine, it seems like it's a pretty consistent one cycle like acknowledgement state. So it's not like the acknowledgement, at least from what we can see, it's not like it has a variable latency that could play into something that could be something you'd have to take into account. So I think
you're
the
saying when you're
consistent.
sitting and waiting for a bus ACK, when you put this into signal tap, you saw that it generally took approximately one cycle to receive that ACK.
You know how in the state machine it has a check for the state and bus ACK equals 1 after after it writes to the bus. That doesn't take any more than one cycle. Like the bus, it doesn't wait any longer for the bus ACK to like toggle, if you know what I mean.
But it could. It depends on what other bus activity there is. For you, that's working because you don't have very much bus activity. You don't have other stuff going on. So for instance, if you were writing the VGA at the same time you were doing the audio, you might find 2 or 3 cycle delay.
Okay. So that depends on whether or not there are other things using that bus.
Right, it depends on the bus load.
Interesting.
And if you're sitting there with one master grabbing data from one slave, there's almost no bus contention. So you're quite right. In this case, it's true, but it may not be generally true.
Okay. That's good to keep in mind for later.
Particularly for lab 3. In lab 3, depending how you set it up, you might have a few bus masters. And if you have lots of bus masters all talking at once, then you can likely expect a little extra latency associated with those bus writes.
Cool.
Okay. Any other questions or issues? I had one question on Piazza asking about, in Model Sim, it appears as if the drum is not damping to exactly 0, but it's getting to some sort of low amplitude oscillations. And that is not an indication that you've done anything wrong. When you discretize the 2D wave equations, you may end up with low amplitude limit cycles. So it may not damp to precisely 0. It may have low amplitude limit cycles that will sound sort of like a very low volume hum. And you can, if you would like, you can have the FPGA detect when it is in that mode, when it's in a low amplitude oscillation mode, and damp that out. That's not strictly required. I'm not gonna make you do that. If you want to do that, you can do that. Zoom might also do that for you. We are finding out. Zoom's background noise suppression may damp out those low amplitude oscillations after a few cycles as well. Which, I mean, that's fine. The Zoom is now sort of an integrated part of this lab. So if you want to use that feature of Zoom to damp out those oscillations, that's fine. Anything else? Okay. Then I'm going to continue talking about lab 3. I will say I have maybe, I don't know how many, maybe this lecture and maybe one more lecture of content that I really want to go over for Lab 3. And then we can talk about what to do after that. I am happy to, if there are specific topics that people would like to hear lectures about, I'd be happy to put together lectures for special topics. If you're interested in doing something specific for your final project, for example. But otherwise, I think quite soon we'll transition to, in lieu of meeting like this to do lecture, we'll increase the amount of lab time. And we'll meet together in labs to continue to work on labs. Okay, so just sort of giving you a heads up that in the not too distant future, I think we'll transition from lecture and lab just to increased amount of lab. And we'll work on debugging Lab 3 and then your final projects. Okay, so let me talk about Lab 3 some more. Last time we talked just about the Mandelbrot set in general, just because it's interesting. But today I want to talk about sort of Lab 3 specifically, and how we're actually going to implement the equations that were presented and talked about last time. So for Lab 3, I'm going to start by just sort of giving an overview of what we're going to be doing, and then I'll zoom into some specifics. So for Lab 3, we're going to be iterating a complex function a lot. And the complex function that we're going to be integrating is this one. Z at n plus 1 is equal to z at n squared plus c, where z at 0 is equal to 0. So for each choice of c, we will determine whether the magnitude of the complex number diverges to infinity or not. If it diverges, it is by definition outside. It is outside. It's outside the Mandelbrot set. If not, it is inside. So specifically, we'll be going through the following process. We will start by choosing some threshold number of iterations to test. We can't obviously run this iteration infinity times to see if a particular choice of complex number diverges to infinity, right? So we're going to choose some relatively large number and iterate it that many times. And if after that many iterations, the magnitude of the complex number has not exceeded 2, you'll recall that for this particular iteration, if z here ever achieves a magnitude greater than 2, then it is going to diverge. It's never coming back. So we'll choose some threshold number of iterations to test, say 1,000, but this will be configurable. So we'll run this iteration for, say, 1,000 times. And if after 1,000 iterations, the magnitude is still not greater than 2, then we'll say, okay, this is probably in the Mandelbrot set. It might not be, but it's an approximation, right? We will map a particular pixel to a C value. Talk about this in a moment. So we'll loop through each pixel, 640 by 480 space, and map that to a particular choice of C, a particular complex number C in a different range. We'll run the iteration for that particular C value. if you reach 1,000 iterations without the complex magnitude exceeding 2, assume that point is in the Mandelbrot set and color it accordingly. If the magnitude of z squared, if the magnitude of z exceeds 2, assign that pixel a color that maps to the log of the number of iterations that it took to reach 2. We'll talk about this too. And then we'll move on to the next pixel. Move on to the next pixel. So we're choosing some threshold number of iterations. We're choosing a pixel. We're mapping that pixel to a particular choice of C here. Running the iteration. If we get to 1,000 iterations and we still haven't exceeded 2, then we say, okay, this is in the Mandelbrot set, and we color that pixel some color that means inside the Mandelbrot set. If before we get to that threshold number of iterations, the value of this complex number, the magnitude of that complex number does exceed 2, then we will color that pixel a color that means outside of the Mandelbrot set. And we'll color it something in proportion to approximately the log 2 of the number of iterations, just because that creates pretty looking color patterns. So visually, that looks like this. So we are choosing a particular pixel on the 640 by 480 screen. That pixel gets mapped to a particular point in the complex plane. So we're going from 640 by 480 to a range of 3 by 2. Mapping, doing a one-to-one mapping of pixel to complex number. We are plugging this complex number into this equation for the iteration, running this iteration over and over and over and over again, and then coloring this pixel in accordance to what happened with this iteration. If we reached 1,000 and we haven't diverged, then we color it a color that means inside the Mandelbrot set. If before we reach that number of iterations we do diverge, then we color it a color which is proportional to the log 2 of the number of iterations that it took to exceed 2. And in actuality, you'll have a few pipes doing this, right? So you'll be doing this in parallel for a few different pixels at the same time. So what makes this interesting is, unlike the drum, different pixels are going to require a different amount of computation, right? For some of these, for points that are inside of the Mandelbrot set, for points that are here inside the Mandelbrot set, you'll be running that iteration 1,000 times to make certain that before you claim that this point is inside the Mandelbrot set and color it accordingly. For other points like out here, for example, this is going to exceed, that complex iteration is going to exceed 2 in like 2 iterations. So in the drum, every one of your parallel pipes had exactly the same amount of computation to do. This time, you need to worry about load balancing, right? You need to think quite carefully about how you are going to divvy up all of these pixels among your various solvers so that each solver has approximately the same amount of computation to do. So this is going to take some thought. We'll talk about some various methods for doing that. There are some sort of naive methods that work okay, and then cleverer methods that work a bit better. You might be able to come up with other clever methods that work really well. But unlike Lab 2, we need to worry about load balancing in this case. So some things we'll have to think about. We will have to think about load balancing among all iterators. We'll have to think about serial bottlenecks. For example, how are you going to dispatch new pixels to each solver? How are you going to dispatch pixels to each solver? Or are you even going to do that? And how are you going to write to the VGA screen from many solvers with limited contention among those solvers? And we'll talk about both of these things. Anything else we'll have to think about? I don't think so. The challenge here is speed, right? The challenge of this lab is just how fast can you draw this, compute and draw this on the VGA screen for a threshold number of iterations of 1,000. And part of your performance grade will depend on how fast you can do this. You'll probably be able to get it done in, what do you think, Bruce? Like 60 milliseconds or so?
60 milliseconds is possible. I think I've seen it down as low as 30 milliseconds, but it depends on some tricks too. And the baseline is, of course, the code I gave you, or Hunter gives you, which will be running on the HPS, which takes like 2 seconds.
Yeah, 2 or 3 seconds.
Gotta be faster than the second.
Okay, so that's at a high level what we're going to be doing. So where to start? As always, start in MATLAB or Python. Build yourself a system in MATLAB or Python, something that you're comfortable in, that you can test and iterate very quickly, so that when you build this iterator in Verilog, you have something that you can compare against to make sure that the Verilog that you've built is correct. Right, so you want to be able to choose a particular value of C, plug it into some MATLAB or Python program, and see how many iterations it takes in order for the magnitude of this complex number to exceed 2. And then make sure that when you run that same algorithm in Verilog, you get the same number in order to convince yourself you've built something that's working correctly. And very thoughtfully, there is some MATLAB on the course website that does just this. So if we take a look at the Lab 3 website, as always, read this Lab 3 webpage incredibly, incredibly thoroughly, just like you've done for the other labs. But there's a lot of information on here that is here to help you. So please make sure that before you get started, read this webpage really thoroughly. But let's just find this MATLAB program. I'll open this up. The MATLAB is really easy to look at because MATLAB knows about complex numbers. So it abstracts away the complex arithmetic that you'll have to actually be wary of in C and in Verilog. But it's a place to start, right? So this is a really simple program. All that it's doing is setting some termination value, some threshold. In this case, this is set to a low number. This is set to 100 so that the whole thing runs more quickly, which is, by the way, something that you are almost certainly going to want to make configurable on the FPGA for exactly that reason. When you're testing, you might want to set that threshold to something like 30, just so that it runs quickly and you can see if things are working correctly, and then you can set it to 1,000 or greater if you want to. It's creating two arrays, x and y, in the range of -2 to 1 for x. This is the real number, the real axis, and then -1 to 1 in the imaginary axis in y. It's looping through each combination of these indices and running this iteration. It's determining whether the magnitude of the complex number has exceeded 2, or if the threshold number of iterations has been reached. And if neither of these are true, then it updates Z, iterates a counter, and runs this again, right? So it runs this iteration on every one of these combinations of indices, and then draws a picture based on the colorized according to the log-based 2 of the number of iterations that it took to exceed 2. So I would start by running this, and this will just generate a pretty picture of the Mandelbrot set. And if you want, you can even change the ranges here. If you want to zoom in on Seahorse Valley or something and take a look at that, I would just start with this. And in fact, let me just put this in the HTML for this class. I don't know if Jupyter does MATLAB syntax highlighting or not. Let's find out. Nope, it doesn't. That's okay. So start in MATLAB or start in Python. Write something that allows you to plug a C in and get a number of iterations out. And then you can compare your Verilog to that. Once you've done that, I would then, I want to show you the C, but let's first review complex arithmetic. Because when we look at the C, the complex arithmetic is not abstracted away from us, because unlike MATLAB, C doesn't know about complex numbers. So we have to implement those things. So let's review complex.
Dirk, can I ask a question?
Yes.
So why do we use the value 2 to check whether it diverges or converges? Because I thought if anything above 1 would at some point diverge.
That was true for when I was introducing the Mandelbrot set. We were thinking about this iteration, which is just repeatedly squaring a complex number and not adding any constant. In this case, if the magnitude of the complex number exceeds 1, then this is unstable. So the region of stability for this iteration was the unit circle centered on the origin in the complex plane. The Mandelbrot iteration is a different iteration. It's this one. It's both, we start with Z0 at the origin, at 0. And it's not just square it, square it, square it. It's square it and add a constant, square it, add a constant, square it, add a constant. For this iteration, it has been shown by, I don't know who, but it has been shown by mathematicians that if the magnitude of this complex number exceeds 2, then it is unstable. This can exceed 1 and remain stable. And in fact, if we look at last lecture, we looked at the approximate region of stability for this iteration, and you can see here that the origin is here. There are regions here that are farther than 1 from the origin that are still stable. But there are no points that are farther than 2 from the origin and that are still stable. If you get farther from 2 from the origin for this iteration, you're never coming back.
Okay. Cool. Thank you.
So we could expand our iteration to the following. I want to separate this into the real and imaginary parts. So we'll say ZR at n+1 plus complex J. I think ECE is like J, right? Complex J ZI n+1 is equal to Zn squared, which we'll write as ZR n plus J ZI n squared, so times that again, plus C, which has both real and imaginary parts. So this is plus the real part of C plus J times the imaginary part of C. Is that clear? So we've taken this iteration and we've just rewritten it. We've represented the square as, we've expanded the square out and we've represented this in, we've separated this into the real and the imaginary parts. Okay. So we could expand all of this, which is to say, FOIL all of this, get it all into one big long expression, and separate into real and imaginary parts to get the following equations, where ZR at n+1 is equal to ZR at n squared minus ZI at n squared plus CR, and ZI at n+1 is equal to 2 ZR at n ZI at n plus CI. Is that clear? So we've taken this iteration. Here we've just separated these imaginary numbers into their real and imaginary parts and written down the exact same equation, just expanded out into the real and the imaginary parts. And then we've expanded this whole expression out and separated it into real and imaginary parts. So we end up with ZR, the real part when you expand this out is you end up with ZR squared is a real number. JZI times JZI is J squared ZI. The definition of the imaginary number J is that J squared is -1, right? So we end up with ZR squared minus ZI squared plus the real part of the constant C. And then we can write down a separate expression that includes all of the imaginary parts. So when we're doing this iteration, we will have some Z. We'll calculate ZRn+1, ZIn+1. Once we've calculated ZRn+1 and ZIn+1, we'll determine whether the magnitude of this complex number has exceeded 2. Actually, we'll determine whether the square of the magnitude has exceeded 4. We don't want to take a square root, right? We don't need to. So instead of checking whether the square root of sums of squares exceeds 4, we'll just determine whether, or I'm sorry, whether the square root of the sums of squares has exceeded 2. We'll just determine whether the sums of squares has exceeded 4. So that will look like this. ZR n plus 1 squared plus ZI n plus 1 squared greater than 4, question mark. And you can take note of something here, which is when we calculate ZR n plus 1 squared and ZI n plus 1 squared, in the next iteration, we can reuse those, right? So when you check this magnitude, when you check to see if your complex number has exceeded this threshold, that will require squaring ZR n plus 1 and ZI n plus 1. So you're going to have to do that. If you just save those values, then you don't have to square them again when you go back up here and recompute for the next iteration. So when we go back and we're computing ZR n plus 2 and ZI n plus 2 using ZR n plus 1 and ZI n plus 1, we've already got these square terms from the previous iteration when we checked this magnitude, which saves you on about half your arithmetic and saves you 2 multipliers, 2 hardware multipliers. So you can drop your number of multipliers from what would have otherwise had to be 1, 2, 3, 4, 5. You can drop your required number of multipliers to 3. Which, if you're using 27-bit fixed point, which is probably right, you'll probably want to use something like 4.23 fixed point, then each DSP block on the FPGA has one 27 by 27-bit hardware multiplier. There are 87 bits, or I'm sorry, 87 DSP blocks on the FPGA. So if you were to do all of those multipliers in parallel, which is the design choice, maybe you don't want to, or maybe you do, then that's something like, well, it's 87 divided by 3 separate pipes. Something like, what, 28, 29? Something like that. So in principle, you could run 28 or 29 of these iterators in parallel. There's enough multipliers to do that. Any questions? So I was going to show you the C, but given that there's only 5 minutes left, I'll do something else instead. And let's just start pondering this notion of load balancing. So suppose that you're building something like 20 iterators. How are you going to divide the pixels up among those different pipes? An option, one that I don't necessarily recommend, is that you could have some sort of central dispatcher that says, you know, to which all of your pipes are communicating, and the dispatcher is asking, are you ready for a new pixel? Are you ready for a new pixel? Are you ready? One of them will say, I'm ready, and then it hands it that pixel. There's a lot of overhead associated with that. I don't necessarily recommend using that sort of technique. Probably what you want to do instead is have every iterator know a priori, before at reset, have it know exactly which pixels it is assigned, and have it go through its pre-assigned pixels so that it's not communicating with some central dispatcher. So then there are a few options for how you might do that, and I have a few of them sort of shown visually here. So let's suppose we have, just for sake of ease of visualization, let's suppose we have 4 parallel iterators. One thing you might consider doing is tiling up the complex plane into 4 chunks and giving a chunk to each of your iterators and asking each one to just blast through your assigned pixels as quickly as you can. The issue with this is if you were to naively divide up the plane like this, well, keep in mind that every point inside the Mandelbrot set is going to take 1,000 iterations. So these two tiles on the right side of the screen have way more points inside the Mandelbrot set than those on the left side of the screen. So these two left side of the screen tiles are going to finish long before these two are, which means you're not going to get the whole thing drawn as quickly as you otherwise might. You want to divide the computation more evenly among your 4 multipliers, or among your 4 iterators, rather. So a better option might be to assign alternating rows to alternating solvers. So we assign row 0 to iterator 0, row 1 to iterator 1, 2 to 2, 3 to 3, and then repeat over and over and over and over and over again. This isn't perfect, right? But it's definitely more evenly distributing the work among these 4 solvers than this was. Another option that works quite nicely is you could divide the screen. Say you have 4 solvers. You could consider 2 by 2 squares of pixels and assign each iterator the same corner of that square of pixels tiled across the screen. So if we look up here in the upper left-hand corner here, there's blue, green, yellow, red. And red is always in the lower left corner. And then we move on to the next tile, and red is always in the lower left corner. This very evenly distributes all of your pixels across the screen, which may do a better job of load balancing than this. Though you could check, right? In MATLAB, you could experiment with a few of these different strategies, have MATLAB count the number of iterations that each of these simulated pipes is computing, and try to get them to balance. Could you come up with better? I've been pondering whether it's not practical, I don't think, but what if beforehand you came up, what if this was assigned more randomly? Is random better than even distributions here? I don't know, there's overhead associated with that, because if it's random, there's not some systematic rule for moving through the grid here. So you need to actually store each iterator's pixels in memory of some kind, which means there's going to be some overhead associated with reading that memory. So it probably doesn't work out better. But supposing that you could get a 0 cycle read from memory, is random, I've been thinking about this and I don't know the answer yet. Would random assignment be better than a regular grid? I don't know. Something I might test because I'm curious. Okay. People have questions?
So the test here would be then, given that it costs nothing to have a random assignment, is the total number of iterations lower? Is the highest iterator lower than it would be for uniform?
Right. Because then statistically, at least the expected number of iterations for all of your iterators would, I think, then be equal. But then you could get unlucky random assignments, right? Like, you would probably want to keep doing this a few times until you ended up with one that ended up, you could end up very unbalanced if you were doing it random, if you got unlucky, I imagine.
The assignment as written currently says you have, it's the time for the whole set plus the time for 2 arbitrary regions picked by the grader. Interesting piece of this is that as you zoom in, the statistics of everything changes.
Okay. I will see most of you in 90 minutes. See the rest of you on Monday.
We figured it out during this lecture.
You got it to work?
Yeah.